All right, as we pursue statistics in the second half of our course here in Math 99, we're going to spend a day today to kind of wrap up the statistical part of it, doing some work with z-scores. Now, when you're dealing with data, you can have all kinds of data. You can have, for instance, say you examine the weight of men at Susquehanna University. You'd have thin little skinny guys, you'd have more normal shaped guys, you'd have great big tough guys, and you'd have all kinds of weights, okay? You could examine shoe size of females at Susquehanna University. You could have small feet, medium-sized feet, big feet. There's all kinds of data. And the amazing thing about what you're going to do for most of you that take Introduction to Statistics, you're going to work with data in such a way that they are all related, in that there's no relationship whatsoever between my weight, my shoe size, the amount of hairs on my head, which get fewer every year. There's no relationship at all between those different things. But if you start thinking about what we did in the last class period, when we talked about the standard deviation, okay? For instance, take shoe size. You have real small shoe sizes, you have medium-sized shoe sizes, you have great big heavy shoe sizes. Big shoe sizes, not, I'm thinking weight, pardon me. So you've got little ones at the left-hand side, okay, for your left is over here. Little ones here, you've got medium ones here, and you got bigger ones over here for shoe sizes, okay? The interesting thing is when you think about standard deviation is a measure of how much spread the data is. If you have data that's really spread out wide, real small ones here, larger ones over here, and so on, you'd have a bigger standard deviation. But what you can do with different data like shoe size and like weight and like number of computers people own or a number of TV sets in a house, what you can do is examine how many standard deviations is a particular data item below the mean, or how many standard deviations is a particular data item above the mean, like a very large shoe size. Very large shoe size is going to be way above the mean and would be 2-3 standard deviations away, okay? Whether it's shoe size, okay, or whether it's the weight of the person, or whether it's the number of TV sets they have in their house. All data can be analyzed, quantitative data can be analyzed by how many standard deviations they are away from the mean, okay? And because of that, because you can do that, you can then answer all kinds of questions about problems. And that's what we're going to be doing today with data. So for instance, let's talk about, for instance, how about IQ? Problem number one. You're going to have people with really, really high IQs. They're going to be over here at the right-hand side. You're going to have pretty much normal folks here in the middle with an average IQ, in which they say average score on an IQ test is 100, okay? So you're going to have scores right around 100. You're going to have some folks over at the left-hand side that have lower IQs, all right? But whether you're talking IQ or shoe size or their weight or the number of TVs that are in each household or the number of kids per family, what you're going to have is even IQs or weight or shoe size, you're going to have some that are many standard deviations above the mean. You're going to have standard deviations that are below the mean, okay? And the way you would do that is you would take the particular data item, okay, minus the mean. You want to find the distance between the data item and the mean, all right? So minus the mean all over the standard deviation, which we're going to represent by that symbol, okay? Now, This symbol is the standard deviation, okay? It's a sigma, small letter sigma. Here's the X bar, which is the mean, okay? When you take a particular data item, and when you subtract the mean, you get the distance between the data item and the mean. Then when you divide by the standard deviation, that tells you how many standard deviations they are away. This formula works for all kinds of data, and that's the beauty of it. All right, so for instance, looking at this problem, the average score in an IQ test is 100. So we know that this is 100, okay? Standard deviation is 16. We know that that is 16. It says find a probability that a student's IQ is less than 112. All right, now here is the average score is 100. So we're going to put 100 right here in the middle. 112 is roughly right about there. 112, okay? We want to know what's the probability that a student's IQ is less than 112. We want this area, okay? And in Introduction to Statistics, you'll get more and more background on this as to why it works and what's going on here. It's kind of beyond the time and the scope of the course that we have now. But this area under this curve is 1 or 100%. If you can find all of these people, right, that have IQs below 112, all right, that's going to give you the probability that a student's IQ is below 112, all right? So here's what we're going to do. We are going to take, we want to be less than 112. So the data item is 112. So we have 112 minus 100 all over 16. Do the math. 112 minus 100 is, of course, 12 divided by 16, which I can do in my head, is 0.75. This is called a z-score. This means, okay, it's a positive 0.75. This means right here that a data item of 112 is 0.75, 75 hundredths, or 3/4 of a standard deviation. Because it's positive, it's above the mean. And you can kind of see that in yourself. If 16 is the standard deviation, 12, a distance of 12, is not a whole standard deviation, it's a fraction of it. So it's the fraction is 0.75. We're not even one standard deviation above the mean. Now the question is, can we find that area? There's all kinds of mathematical ways you can find that area. There's a great way to do it in calculus, all right? But we're not going to be doing calculus here. We want to figure out a way to find that area, and that'll tell us what the probability is that a student has an IQ below 112. And the beauty of this is someone has already figured this out for us, okay? If you, and you will have this supplied to you, it's either in your handout or it's going to be attached to your work today. If you look at this, and by the way, it's going to be almost impossible for you to see that. I can basically show it to you now, and you can look off of your copy as we're going through these problems. But this is all the z-scores. This column tells you the z-score here is -3.4, -3.3, the whole way up to 0, okay? And then here are the hundredths, like -3.41 would be right here, okay? This, the body here, gives you that area that we're looking for, okay? So that's the beauty of it. If you can find this z-score, how many standard deviations away, you just look up on your table. So we found the z-score is a positive 0.75, and I told you those z-scores were negative, so we've got to go down and find the positive one. Let's go down here, okay? And here we are with the positive z-scores. Here's 0.7, and here is 0.75. Right over 0.75 is right here is 0.7734, okay? That tells me this area right here is 0.7734, or 77.34% of all students have an IQ equal or strictly less than 112, I guess is what it was in this problem. So the steps are, you should draw a picture, you should figure out your z-score, then look it up to be able to answer the question. 3 steps in every problem. And you will do tons of these problems when you take STAT. All right, so let's go back to the problems. How about we want to know the probability that a person has an IQ bigger than 110. So let's draw a picture again. Here's the picture. Here's 100. Here's 110. We want this time bigger. It's the other side. Okay, bigger than 110. So let's find the z-score. The z-score would be 110 minus 100. Remember, it's x minus x bar all over sigma, the standard deviation of 16. So that would be 110 minus 100 is 10 over 16, which is 5/8, which should be 0.625, I think. 10 divided by 16. Yeah, is 0.625. Or, because the chart we're using only goes to hundreds, I'm going to round that off to 0.63. All right, so we're ready. Go back to your chart. Okay, go to your chart. And I want a positive 0.63. Positive, here's 0.6. Go over to 3 is 0.7357. So 0.7357. Now remember, the chart gives you the area going this way, okay? We want the area bigger this time, right? So if the whole area, as I mentioned a little bit before, is 1, you can subtract that off of 1. So 1 minus 0.7357 equals 0.2643, or 26.43% of students have an IQ bigger than 110. And I would think that percentage is a little higher at SU because you guys are bright. Okay? All right. Let's do another. So go back to the problems. Part C. We want to be between 116 and 132. Okay? So draw a picture. So here we are. 100 is the average here. We want to be between 116 and 132. We want just in there. That's it. So we're going to have to do 2 z-scores. I've got to do 116 minus 100 all over 16. And I've got to do 132 minus 100 all over 16. All right, let's get them both. This should be pretty easy. 16 divided by 16 is 1. And over here, this is 32 divided by 16 is 2. So now let's go back to our chart. And did I lose it? Oh, shoot, I lost it. So let's find z-scores again. Sorry. I'm going to need a table. Okay, there it is. Now, so we've got to find 1 and 2. Okay, 1 and 2. So here we are at 1.0 right here. 1.0 is an area of 0.8413. So for the 1, which is right here, this is 0.8413 to the left. And then 2 is down here, 0.9772 is the area to the left of that one. So you want to take those two areas and subtract them, and 0.9772 minus 0.8413, and I get 0.1359, I'll change it to a percentage right away, is 13.59%. Okay? Are you sticking with me on how these work? All right, see if I can go back without losing it. And what happened to my cursor? There it is. All right, so let's go down to problem 2. Okay? The average 6th grade girl is 60 inches tall with a standard deviation of 3 inches. Okay? What percentage of 6th grade girls are less than 57 inches? All right, here we go. So we have the average is 60. So here is 60. Okay, standard deviation is 3. What percent of girls are less than 57? 57 would be down here. So we want this small region there. Okay, so we are going to do x minus x bar all over the standard deviation. So it's 57 minus 60 all over 3. Yeah, and this one should be pretty easy because the top is -3 divided by 3 is -1. So we know that 57 is 1 standard deviation below the mean because it's negative. All right, so let's go back to our table. See if I can do it without wrecking the table this time. Okay, so we want -1. So I'm going to have to go back up to this chart where there's negatives, and I want -1.0 is right here. Exactly, -1.0 is 0.1587 or 15.87%. Not very many. Not very many girls are less than 57 inches. Okay? How about part B? What percent of girls are greater than 63 inches tall? Okay, so let's go up to our same picture. Up here, this is 63. We want this side over here. Okay, so set it up again. 63 minus 60 over 3. This time is a +1. Okay? Now we're going to have to be careful because it's above 63. So go back to your chart. Go back to your chart. And we want +1, which I think we did that one before. +1 is right here, 0.8413. So we know, now remember, the chart gives you areas to the left. So this area from here down is 0.8413. And remember what we did the last time? When you had one that was above, the whole area is 1 or 100%. So we have to take 1 minus 0.8413, and I get 15.87. It's exactly the same. This is what's cool. It's exactly the same percentage of girls that are taller than 63 as there are girls shorter than 57, because 63 is 1 standard deviation above, 57 is 1 standard deviation below. Isn't that cool? Right? All right. Okay, so go back and go down to problem 3. The average stopping distance. All right, so let's erase. I just love statistics. The average stopping distance for a car is 70 feet. So I know, draw our picture. Here is 70. Traveling 40 miles per hour. Assume the standard deviation is 5 feet. So I know the standard deviation is 5. What percentage of cars can stop within 75 feet? So 75 would be about here. What percentage of cars can stop within 75 feet? In other words, stop at 75 or smaller. So we want this area coming down. Okay, so you set it up exactly the same way again. 75 minus 70 all over 5, right? 75 minus 70 is 5, divided by 5 is 1. And we can probably go, remember the answer from the last problem. Wasn't it 15.87% when we looked up the, 15.87 would be bigger than 75 or less than 65. We want from 75 the whole way down, okay? So you can look it up, or you could just subtract 15.87 from 1 to get that side. Let's look it up just to keep everybody on the straight and narrow here. Okay, look it up. We want a positive 1, and a positive 1 is right there, 84.13% can stop within 75 feet, okay? How about if I said, what percentage of cars can stop within 71 feet? Within 71 feet. Now, because this is dead in the middle, you would think stopping within 71, it should be reasonably close to 50%, right? But we'll see, okay? So let's check it out. This would be 71 minus 70 all over, it was 5, wasn't it? Is 1/5 or 0.2. I want to double check that. I was thinking of stopping within, standard deviation was 5 feet, right? Yeah. Okay, so let's go back to our chart. And we want to look up a positive 0.2. So here I am on the positive chart. 0.20 would be right there, 0.5793, and it's reasonably close. 57.93% of all cars can stop within 71 feet. Okay? One more strange one. How about if I said, what percentage of cars would require more than, let's say, 78 feet? Okay, let's do that. Here we are again. Here's the average stopping distance is 70. What if I said, what percentage of cars take more than 78 feet? 78 is way over here. And you're going to bet it's not going to be very many because most of them are stopping within around 70 feet. So we're going to do 78 minus 70 all over the 5 is 8 divided by 5 should be 1.6, I think. Okay, 1.6, and if you look up 1.6 is right here. It's 94.52% of the cars. Remember, what if this would have come out to have been 1.67? If it would have come out to be 1.67, you go down to 1.6, and then you go over to the 7, which is right there. It'd be 95.25. Okay? And that's the way that works the chart. And that is also the way you do z-scores and statistical analysis. Pretty great stuff, right?